start with the first one, and that will be on a project that has happened at the Große Welle Canal in Germany. So I would like to ask Franziska Ruprecht, yes, to come forward. She is a PhD fellow at the University of Hamburg, and as I understood, the experiments were started or happened in the autumn of last year. But already they have some very interesting results that will be presented to you now. So please, we only have one microphone, so I have to run a bit back and forth.
So yeah, welcome everybody. Yes, my presentation will be on wave dissipation by salt marshes, as Alexandra already said. And of course, I'm presenting not only my own work, but the work of our whole project group. Okay. Yeah, the outline of my talk will be as follows. I will first give a short introduction on salt marshes and wave energy dissipation, and then I will introduce you to a large-scale flume experiment we conducted on wave dissipation by salt marshes under extreme wave heights and water levels. And finally, I will end my talk with a short outlook on further research. Well, salt marshes, as you can see, are intertidal ecosystems, and they fringe many of the world's shallow coastlines. They provide us with a range of services, such as carbon storage, habitat provisioning, and also coastal protection. Salt marshes can contribute to coastal protection by the dissipation of wave energy, by the stabilization of shorelines, and by the reduction of storm surges. Well, following sea level rise and increased storminess, there's a growing political interest in services provided by coastal ecosystems and also in their role as cost-effective components of coastal defense schemes. At the same time, there's also mounting scientific evidence for wave and surge dissipation by salt marshes. And review studies, for instance, highlight that wave energy dissipation over vegetated surfaces is significantly higher than over bare mudflats. And further, another important insight is also that wave energy dissipation is highest for shortest distances from the seaward marsh edge compared to equivalent landward distances. A very important knowledge gap in the whole research field is, however, that all of the existing empirical studies are limited to average hydrodynamic conditions, that is, to shallow water depth and also low wave heights. And so we know nothing about how much salt marshes can contribute to wave energy dissipation when it matters most, that is under storm surge conditions. Yes, the most important controls of wind wave dissipation are now recognized. The height of incident waves, then height of vegetation, density and stiffness of the vegetation, and the salt marsh geomorphology. So just to illustrate briefly, then the waves that were shown here schematically travel over the marsh surface. Then the orbital wave motion beneath the waves is interfered with the vegetation, and consequently the wave energy is dissipated by the transfer of the kinetic energy from the waves to the vegetation canopy and the marsh surface. And the amount of orbital wave motion that can be interfered with the marsh surface increases for a given wave height with decreasing water depth, and also with the height of incident waves. And so it is reasonable to assume that if height and energy of incident waves pass a critical level, then the salt marshes may lose their protective effect because the plant canopy is uprooted and broken, and the marsh surface will be eroded. And knowledge on such thresholds is critical to assess the wave dissipation capacity of salt marshes under storm surge conditions. Yeah, and this leads us to the aims that we had in our large-scale flume experiment on wave energy dissipation under extreme wave heights and water levels. Our first key aim was that we wanted to explore the transition from wave energy dissipation to wave energy transmission over vegetated salt marsh surface. And second, we wanted to quantify the response of the vegetation and the soil surface to the incident wave energy. We conducted this experiment in the large wave flume of Forschungszentrum Küste in Germany. And this flume has a length of 300 meters and a width of 5 meters and a depth of 7 meters. First step of the experiment was, of course, to get the salt marsh, and we excavated 200 square meters at the mainland coast of the German Wadden Sea. We cut the salt marsh in small blocks by the help of this digger, and then we placed the blocks on Euro pallets and transported them to the wave flume. Yeah, and there we reassembled the blocks, and as you can see on this schematic drawing, we had a vegetated test section in the flume of 14 meter length, and this test section was preceded at the front and rear end by a berm made of concrete to allow the waves to shoal or to break. And over this whole test section, we deployed 16 wave gauges to measure the dissipation. So this is just to give you an impression of the situation in the flume during the setup of the experiment, and the link is a time-lapse video on YouTube. I will also show it later again, the link. Our schedule for inundation and the measurements was as follows. We simulated 2 water depths, 1 and 2 meters, and 7 different wave heights from 10 centimeter to 90 centimeter. And then we conducted tests for regular and irregular waves. And during these tests, we recorded also the movement of plants here with video cameras deployed behind an observation window. Every 2 days, we drained our tank, and also we collected the released biomass to quantify the biomass that remained on the test section. And during the times of flume drainage, we also performed measurements of soil surface lowering. Well, and in the end of our experiment, we mowed the whole test section, and then we repeated selected wave tests to quantify the effect of the vegetation on the measured dissipation as opposed to the topography of the marsh, the surface. So this is just to show some results. The figure shows the wave dissipation in 2 meter water depth for regular waves. We have with the closed diamonds the dissipation over the intact vegetated surface, and the open diamond is dissipation over the mowed surface. What we can see is that initially the dissipation increased from 0 dissipation to around 90% for wave height of 30 centimeter. And then we have a decrease in dissipation for waves that exceeded 30 centimeter to around 14%. And in the end, for the wave tests with the largest waves, the dissipation increased again, but yeah, this was due to wave breaking. And here, at the time of the maximum measured dissipation, we see that the dissipation over the mowed surface was lower than over the vegetated surface by a factor of around 0.4, and this means that the vegetation accounted for around 60% of the dissipation that we measured. I already said that we also measured the soil surface lowering and the biomass on the test section, and these blue lines mark the times when we drained the flume to perform these measurements. And here you can see some results. We have the light gray bars. It's the dry weight of the biomass remaining on the test section. And the narrow dark gray bars indicate the soil surface lowering. And here we have the sample date from the start of the experiment to the end. And again, what we see is that the biomass was reduced by around 30% after 2 days of wave tests with these higher wave energy conditions. And with respect to the soil surface lowering, we can say that the lowering from one measurement to the next was the highest in the end of the experiment. But in total, the soil surface lowering was not significantly different from zero. So the next slide will explain a little bit more in detail why we have this decrease in wave dissipation for waves higher than 30 centimeters. The analysis of our video footage showed that this reduction dissipation was accompanied by a change in plant behavior. In this figure, we have the situation of 30 centimeter wave height, and on the right you see a video time frame, and that indicates the stem extension, and here the bending of plants during the wave forward motion. And on the left, the water level and the stem extension is plotted against time. And what I want to show is just simply that the vegetation, which is the gray line, sways with the water level. This is the black line, and so interacts with the waves throughout the wave cycle. And in this situation, the transfer from the kinetic energy from the waves to the plants is the key mechanism for the wave dissipation. This figure shows the situation with waves with a height of 40 centimeters. We see in the video frame that the stem extension is now longer as the plants are bent to wider angles. And this means that for part of the wave cycle, just the flow could travel over this flattened canopy rather than interacting with it. And so the flow retained more energy, and we measured a reduced dissipation. So, yeah, what can we learn from all these observations? Yeah, the first aim of the experiment was to explore the transition from wave energy dissipation to wave energy transmission over our 40-meter vegetated salt marsh section. And we found with our experiment that dissipation was maximum 20%, and that regular waves of around 30 centimeters and irregular waves of 40 to 60 centimeters were less efficiently dissipated than waves around these heights. With respect to the response of the salt marsh vegetation and the soil surface, we found that neither vegetation nor the soil surface was significantly damaged by the high wave energy. To conclude, we can say that the salt marshes still contribute to wave dissipation under storm surge conditions, and that vegetation accounts for a larger share of this contribution, and that the process transitions exist for wave dissipation that can be associated with specific levels of the energy of incident waves. All these findings are a step forward to find an appropriate way how we can include salt marshes in coastal defense schemes, and how realistic their contribution is. And further research, of course, is required. Next important step would be the validation of established models for wave dissipation with our data. We are already working on that. Then we need improved quantification of the vegetation-induced drag. For this purpose, we need improved measurements of the relevant vegetation characteristics, such as structure and stiffness. And then finally, we need just to upscale all these parameters to the landscape scale. And I just want to mention shortly is a new project called FAST. And some members of our project group are also involved in this project. And there we try to detect the foreshore stability and the vegetation-induced wave dissipation from space. So thank you for listening. And if you want to see more photographs and have more information on the experiment, then you can check the blog on wordpress.com. Thank you.
Thank you very much, Franziska. I think we have time for some questions, so I would invite all of you. I hope, yeah, a lot of people here, so there should be a lot of things. Okay, thank you.
Thanks for the presentation. Perhaps I missed some part of your presentation, so that's the reason probably about this question. You mentioned that you have been varying the wave height to evaluate the dissipation of the patch. Did you change the wave period? Because I can't catch which is the wave period you use and which is how many wavelength do you have inside the patch, or which is, in order to understand much better, which is the dissipation. Thank you.
Yeah, of course, we had the different wave periods also. They had these 2 water depths, 7 wave heights, and then, I don't know exactly, I think 5 or 6 periods also. And the highest period was 5.1, and the shortest one, I have to look it up, I can check it in the paper, but different wave periods, of course. Yeah, I think so, but I think most, it has something to do with it, yeah.
One more question? Okay, that's it. Okay, other questions? Yeah. So you only have one microphone?
Just to clarify, you say that 20% reduction, that's 20% reduction in 40 meters, isn't it? Okay, thank you.
Yeah, I understand that right, that there is also some loss in dissipation due to damage of the plant cover. I was wondering, on the long run, does the plant cover recover and regenerate, or do we have a permanent loss?
So this loss, I think, is not a great pity, because the roots were not damaged. I think you have substantial damage and the root mat is damaged, because then the plants can't regenerate. And we know from the natural environment that in the winter, for instance, there's a die-off of 60 to 70% biomass, and the plants regenerate very quickly. So this is not substantial damage, this 30%.
Those who have questions should sit a bit more to the front.
I'm going to be maybe a bit picky on this one, but if you are looking at the 5% reduction in the dissipation, that trend is due to a single data point, and I think there's different wave periods represented in this whole plot as well. I would probably go up, and then I would go horizontal, and then I'd go up to wave breaking. That would probably be a better description of the empirical data, I think.
That's more a comment. I don't know if you want to reply on that. Okay.
Maybe I can answer that question, because if you plot the same thing on wave energy, you will get the same trend. It's a bit more scattered then, but we within the group believe that there is still a dissipation going on in there, even though you consider different wave periods.
Okay. Yeah. More?
And not a question about graphs, but more about how this relates to things you see in the field in terms of the waves you used, and also the geomorphology of the plot you used. It seems very flat, whereas you walk on a real salt marsh, there's always a lot of bumps and stuff. And if I understood correctly, I followed the blog a bit. There was also somewhere in this year a big storm, which was also measured on a salt marsh in England, wasn't it? I don't know if you know anything about it, but I would be interested to hear how these results compare to real field situations.
Yeah, first, of course, the conditions we simulate because we know that during the storm surges, for instance, the above marsh water depths reach or even exceed the 2 meters, and also waves for more than 80 centimeter height are not unrealistic. And I think this matches with these observations from the storm in South England. There's a publication on that, very short, I can show you. And what was the second question? On the topography, yeah. It was not as flat as it looks like from above. So we had quite some variation in the surface because the blocks were not very even. So I think the surface corresponds more or less as far as possible to the natural conditions. But of course it's an experiment. So
maybe I have one last question myself, because this morning too we heard about the transfer of plants in the tanks and everything, and in your article too you say that the behavior of the plants is quite critical for how they react to wave dissipation. But did you feel that there was a change, I mean, compared to the light intensity maybe, or the temperature that these plants experience in a flume compared to the field?
yeah, of course, there's a big difference, and this I feel that there's a very big difference. But yeah, we tried our best to quantify the difference between the vegetation in the flume and the vegetation in the field in terms of stiffness and also biomass. And there is a difference, but yeah, it was a big challenge to conduct this experiment in any way. And so we could not avoid that it's not perfectly natural. But at least we can say how much the difference is. So.
Very good. Then I think we will stop here. Thank you very much again for your excellent presentation. Okay, then we will move forward to the